Welcome to IT.Solution, your total network, system, firewall, and security partner.
All right, let's jump right into this explainer for SRWE Module 6 and crack a classic networking puzzle. How exactly do you get massive network speeds without breaking everything in the process? Today, we're completely demystifying EtherChannel. You know, if you've spent even a little time wrangling switches, you've probably hit this exact wall. How do you crank up the bandwidth between two switches without accidentally triggering a catastrophic switching loop? Because as we all know, simply plugging in a bunch of extra cables just sets off spanning tree protocol, right? STP swoops in, doing its job to save us from loops, of course, but it instantly blocks those redundant links. And frankly, in today's networks, we desperately need that extra pipeline for heavy traffic. So here's our game plan for today's explainer. We'll start with why we actually need EtherChannel, then compare the PAgP and LACP protocols, figure out how load distribution works under the hood, and finally, we'll roll up our sleeves for some configuration, verification, and a little troubleshooting. Okay, part 1. Let's look at the absolute necessity of EtherChannel and link aggregation. This visual really hits the nail on the head. We are essentially pulling a fast one on spanning tree. Instead of seeing, say, 2 or 4 separate cables, which it would normally just shut down to prevent a loop, STP is presented with one massive combined virtual pipe. We call this a port channel. We're just taking those physical links and bundling them together into a single logical connection. And the benefits here are just huge. You can group up to 8 active physical links together. Since spanning tree only sees that one logical link, you completely avoid blocked ports. That means you can achieve up to 8 gigabits per second with a gigabit EtherChannel. But honestly, the real magic, it's the instant redundancy. If someone accidentally unplugs a cable or a wire goes bad, the logical link stays up. You get fault tolerance instantly without having to wait for STP to go through its whole recalculation phase. Moving on to part 2, let's talk about the rules of engagement. PAgP and LACP, our auto-negotiation protocols. Because let's face it, you can't just plug these things in and hope for the best. Before the channel even forms and starts moving your data, the switches have to talk it out using auto-negotiation protocols. They fire specific packets back and forth across those physical links just to double-check that configurations like speed, duplex, and VLANs match perfectly on both sides. If they don't see eye to eye, the channel simply won't form, which is actually a great safeguard against network errors. Now, if you're prepping for a certification exam, definitely burn this comparison into your brain. On one side, we've got Cisco's proprietary protocol, PAgP, which uses the modes desirable and auto. On the other side is LACP. Now, LACP is an IEEE standard, making it your go-to for multi-vendor environments. It uses active and passive modes. Plus, LACP has a really clever trick. It actually supports up to 16 links in a bundle. 8 of those are actively passing traffic, while the other 8 wait on standby, ready to tag in instantly if an active link drops. And speaking of exams, this table right here is pure gold. It lays out exactly which mode combinations will successfully bring up a channel. If you hardcode both sides to on, the channel just forms, no dynamic negotiation needed. If one side is actively trying to negotiate using desirable or active, and the other side is either actively trying to or just passively listening, boom, you're good. But pay attention to that bottom row. If both switches are just sitting there passively in auto or passive mode waiting for the other guy to start, well, the negotiation never kicks off, and that channel is never going to form. All right, part 3, EtherChannel load distribution. Let's look at the forwarding logic. So, our massive pipe is built, but how does the switch actually direct traffic across it? Once that port channel is up, the switch has to mathematically decide which specific physical wire inside that bundle gets which frame. It uses EtherChannel load distribution algorithms to make sure the traffic is shared evenly. We definitely don't want one cable doing all the heavy lifting while the others just sit idle. To pull this off, the switch has a few methods to choose from. It can look at the source MAC address, the destination MAC address, or maybe a combination of the two. It can even peek into layer 3 and layer 4 headers for IP addresses and TCP or UDP ports. The really smart part? The switch focuses its math on the low order bits in those headers. Why? Because in real-world traffic, those low-order bits are the ones changing the most frequently, which guarantees a much more balanced spread across your links. Plus, this specific hashing method guarantees that a single application flow will always take the exact same physical path, which keeps your packets from arriving out of order. Okay, on to part 4, configuring your EtherChannel. Let's get into the guidelines. Enough theory, let's actually build one at the command line. This 3-step process is literally your blueprint. Step 1, grab the physical ports you want to bundle using the interface range command. Step 2, bind them all to a channel group using your protocol keyword. In this example, by typing mode active, we're explicitly telling the switch, hey, use LACP. And step 3, apply your layer 2 settings directly to that newly created logical interface. You type interface port channel 1 and then follow it up with your commands, like switch port mode trunk. Just remember, the port channel interface is the boss now. You apply your VLAN and trunking settings there, not on the individual physical ports. Finally, part 5, verifying and troubleshooting common channel issues. Because let's be real, in networking, things will inevitably break. When they do, show EtherChannel summary is going to be your absolute best friend. If you run that command and see a big old D flag next to your fast Ethernet ports, that means down. You know right away your channel has failed, and 99% of the time it's because there's a configuration mismatch somewhere between those two switches. When that happens, you need to aggressively run through this checklist on both switches. First, do all the interfaces even support EtherChannel? Next, and this is a big one, port speed and duplex modes have to match perfectly. We all know the headache of a duplex mismatch. Also, your VLAN assignments and allowed trunk VLANs must be absolutely identical on both sides. If there's a single mismatch in there, it fails the compatibility check and the switch throws that port right into an error state. But let's say you play detective, found the mismatch and fixed it. This is what a healthy channel looks like. Notice the SU flags next to port channel 1. The S tells us it's a layer 2 channel, and the U means it's currently in use. Over on the right, those P flags confirm our physical fast Ethernet ports are successfully bundled. That is exactly what you want to see. So now that you know how to outsmart spanning tree and bundle your links with EtherChannel, I'll leave you with this to chew on. As networks scale up exponentially to support massive cloud traffic and software-defined architectures, how will you use these principles to guarantee absolute zero downtime in your own environments? Think about it. How can you build a network so resilient it never drops a single packet? Thanks for joining me on this explainer, and keep...
Thank you for watching. See you in the next episode.